Thank you very much for the invitation. So my talk is going to be about exact Borel subalgebras of quasi-hereditary algebras and more generally of standardly stratified algebras. And the idea is just to give an overview of this very special class of subalgebras. And in order to introduce this special class of subalgebras, I'll start with, sorry, I cannot manage to move to the next slide. Okay, good. I'll start by establishing a parallel with a classic result in algebra, which is Wedderburn-Malthus theorem. But before doing so, let me fix some notation. K is going to be throughout an algebraically closed field, and A is going to be our underlying algebra. And I must say that by algebra, I mean a finite dimensional algebra over the underlying field K. Now, what does Wedderburn-Malthus theorem say? It says that any algebra has a maximal semi-simple subalgebra. That's an existence statement. But it also says that given any two Morita equivalent algebras, let's say A and A prime, such that A and A prime both have a basic maximal semi-simple subalgebra, let's say S and S prime respectively, then in that case, A and A prime must be isomorphic, and there is indeed an isomorphism from A to A prime, which restricts to an isomorphism between the maximal semi-simple subalgebras S and S prime. And we shall see shortly that something very similar happens for quasi-hereditary algebras, and I would say it's expected to hold for standardly stratified algebras. Now, let me recall the definition of a standardly stratified algebra. And for that, we need to fix a set phi, which is going to denote the isoclasses of simple A modules. For every I in phi, as usual, we are going to denote by Li, the simple A module with label I. Pi is going to be the projective cover of Li, and Qi is going to be the injective hull of L of I. If phi is then endowed with partial ordering, then we can define the notion of a standard module and also that of a costandard module. So the standard module with label I, delta I, is the largest quotient of Pi with composition factors of the form Lj with j smaller or equal to 1. The costandard module with a label I, nabla I, is defined dually as a submodule of Q of I, but we also have the notion of a proper standard module. These are denoted by delta I bar. And delta I bar is simply the largest quotient of delta I, such that the composition factor Li appears just once. And similarly, we have the dual notion of a proper costandard module. Now, what is less standardly stratified algebra? We say that A is less standardly stratified with respect to our poset phi if for every I in phi, the kernel of the canonical epoch from P of I to delta of I is filtered by the modules delta j with j greater than I. And A is said to be quasi-hereditary if it is not only less standardly stratified, but also the standard modules coincide with the proper standard modules. Now, we want to establish this parallel with Wedderburn-Malthus theorem. And in order to do so, we need the counterpart of a maximal semi-simple subalgebra in the setting of standardly stratified algebras. And the correct notion for that is that of a regular exact Borel subalgebra. So what is that? A subalgebra B of a less standardly stratified algebra A is an exact Borel subalgebra if the following conditions hold. First, we want the induction functor to be exact from B mod to A mod. Secondly, we want that the simples over B are in bijection with the simples over A, and we want that B is less standardly stratified with respect to phi and has simple standard modules. And lastly, we want that inducing up the simple module over B with label I yields the standard module over A with label I, and that should hold for every I in phi. Now, we say that B is regular if it is a homologically well-behaved exact Borel subalgebra. So in that case, we require that these X groups over here are isomorphic for every I in J in phi and for every N greater or equal to 1. Now, unlike the case of Wedderburn-Malthus theorem, it's not true that every left standardly stratified algebra has an exact Borel subalgebra. However, they always exist up to equivalence of less standardly stratified algebras. What do I mean by that? I'm going to say that to less standardly stratified algebras, A and A prime are equivalent if there exists an equivalence between the corresponding categories of modules filtered by standard modules, which preserves the canonical exact structure of such categories. And now we come to the existence result about exact Borel subalgebras, which is due to Koenig, Külshammer, and Dovizhenko for the quasi-hereditary algebra case, and Bautista, Perez, and Salmeron for a more general situation, which includes the less standardly stratified algebras. The result says the following. It says that every less standardly stratified algebra is equivalent to another less standardly stratified algebra, say A prime, such that this A prime contains an exact Borel subalgebra. So A may not contain one, but it's equivalent to another one with A prime, which is guaranteed to have an exact Borel subalgebra. And this exact Borel subalgebra in the theorem may be required to be regular. The theorem is still true. And in fact, we may also ask it to be basic. And now we inquire whether such an algebra A prime equivalent to A and containing a basic regular exact Borel subalgebra is unique. And the answer is yes, such an A prime is unique up to isomorphism. And in fact, a stronger result holds for quasi-hereditary algebras. This result is due to Külshammer and Mimitz, and it says the following. So let A and A prime be two equivalent quasi-hereditary algebras, and let's assume that they have both a basic regular exact Borel subalgebras, let's say B and B prime respectively. Then in that case, A and A prime should be in fact isomorphism, and there exists an isomorphism from A to A prime, which restricts to an isomorphism between B and B prime. And this should remind us a lot about what we have seen in Wedderburn-Malthus theorem. Now, as I mentioned before, not every left standardly stratified algebra has an exact Borel subalgebra. So we may ask which of them do have such subalgebras. And there's a relatively simple answer to this question. There exists an algorithm which takes as input the composition factors of the standard modules, the composition factors of the proper co-standard modules, and also the dimensions of the Hom spaces between the standard modules, and as output produces a matrix which we shall denote by V. And this matrix V can be used to answer the question above. So if A is less standardly stratified, then A has a regular exact Borel subalgebra if and only if the unique solution of this linear system of equations over here is a vector with entries in N. Moreover, the matrix V can be used to compute the Cartan matrix of regular exact Borel subalgebras. Namely, if B is a regular exact Borel subalgebra of some algebra equivalent to A, then the Cartan matrix of B is given by the transpose of this matrix multiplication over here. And now for ease of reference in the next slide, we shall denote this matrix multiplication over here, which is then transposed by CB of A. We have seen before that it's hard to check whether an exact Borel subalgebra is regular. One would have to verify that all these X groups are isomorphic for n equal or greater than 1. So this prompts the question whether there is some easy criteria to decide if an exact Borel subalgebra is regular. And unfortunately, we just have an answer for this in the case of basic left standardly stratified algebras. Together with Steffen Koenig, we have proved that if B is an exact Borel subalgebra of a basic left standardly stratified algebra A, then the following are equivalent. B is regular. The radical of every standard module is filtered by proper co-standard modules, and the Cartan matrix of B is the matrix CB of A that we have seen before. And to finish, I would like to address the question of compatibility of exact Borel subalgebras with idempotent quotients and idempotent subalgebras. So classically, if we pick an idempotent E in A, it induces a recollement like this one over here. And if A is less standardly stratified and we pick the idempotent E at random, of course, we should not expect that the idempotent quotient over here and the idempotent subalgebra over here are still less standardly stratified, nor that the recollement preserves the standardly stratified structure. For that, we need idempotents which are compatible with the standardly stratified structure. Let me define a couple of things. We'll define the essential order for the algebra A as the minimal partial order on phi containing all pairs ij, such that either Li is a composition factor of delta j or Li is a composition factor of nabla j bar. We'll define the support of the idempotent E in A as the set of all elements I and phi such that E times L of I is non-zero. And finally, we say that the idempotent is compatible with the less standardly stratified algebra A if the support of E in A is an upper closed subset of this poset over here. So the support of E in A should be a co-ideal of this poset. Now about the compatibility with the exact Borel subalgebras, there's the following theorem together with Julian Külshammer. Let P be an exact Borel subalgebra of a less standardly stratified algebra A, and let E be an idempotent supported in an upper closed subset of phi. Then it turns out that the idempotent subalgebra EBE is still an exact Borel subalgebra of the corresponding idempotent subalgebra of A, and something similar holds for the idempotent quotients. And if moreover we ask for B to be regular, it turns out that the idempotent subalgebra and the idempotent quotient subalgebra are moreover regular, and one can weaken the condition on the idempotent E and just ask it to be compatible with A. And finally, for A less standardly stratified and E compatible with A, we get that the previous matrix V as a lower triangular block structure, where here we get the matrices V corresponding to the idempotent quotient and the idempotent subalgebra. Yeah. Thank you very much for your attention.